So when is our exam?
Tomorrow.
Okay, I hope not tomorrow. I have to write it tomorrow. It'll be next Thursday. I'll get out a review sheet. I'll probably be sending it to you over the mail, and you can look at it there. Pretty much, what it's going to end with what we did last time. So the really scattering will be the last thing on the exam. And what we want to do today is I want to show you the demonstration, but I don't have it set up. So I want to start the idea of polarization, and then we want to start getting, I want to show you how you can start making circular polarized light, all these kind of really neat ideas. So I want to talk about polarized light. And I'll try to convince you when we do the Rayleigh scattering thing. Rayleigh scattering is going to give us polarized light as well. Okay, so what this is going to mean is that transverse wave. Okay, what does it mean to be transverse again?
It's up and down, perpendicular, no?
Yeah,
Maybe perpendicular.
that whatever is being displaced,
Yeah.
okay, is perpendicular to
The direction of motion.
the direction of motion. The transverse wave is basically the displacement. I'll put this in quotes. Is perpendicular to the direction of motion. So let's say I have a string here. Here's a string. And I'm going to send this through a fence. So here's the fence. Here's the, I'm going to send it through a fence like this. So these are fence posts. So if I take the string and kind of go all crazy with it like this, okay? So the string is going all over the place. When that hits this fence post, what's going to happen? How's the string going to look afterwards? Yeah, basically you can have all these weird motions like that, but that's not going to get through for the most part. What's going to happen? Any motion going like that, that'll get through. So when you're done with this, you're only going to get motion like this, basically along that same direction here, like this. If I take this and shake it in some sort of, well, I don't know what that would be. Okay, some sort of convoluted fashion here. This convoluted part of going like this is not going to get through here. When it comes through here, it's all going to be oscillating in one direction. So when this is all oscillating in one direction, you call that polarization. So the displacement here, all the displacement in the perpendicular direction for the propagation is in one direction. Okay, can you even talk about a longitudinal wave being polarized? No. Longitudinal waves can't be polarized. So okay, I don't necessarily recommend this, but okay, if you go to a physics meeting, one of the big physics meetings, they always have a crazy section. And I'll tell you what, this is probably an apocryphal story, but this is what it is. Okay, so the claim is that one time somebody wanted to give a talk, and they submitted basically the work for a talk. And they said, no, you're crazy. You can't give a talk here because you're nuts. And then the guy came back with a gun and went, okay, here's where you can talk. And then the crazy guy gave a talk. And so now what they do is that if somebody submits a talk and it's crazy, they won't reject them. They take all the crazy talks and they put them together. They don't call it the crazy talk section. They give it some title. And then basically anyone who's a physicist who looks at this title realizes, oh, this is the crazy section. And so when I've gone to these meetings, a lot of the younger faculty physicists would go and actually go to the crazy talks because they were entertaining. And so there was this one guy, his name, I mean, he's harmless. His name was Wagner. And Wagner discovered actually Wagner waves. That's lucky. And it turns out there's an integral number of Wagner waves in a stalk of corn, and an integral number of Wagner waves between the Earth and the sun. And it turns out that they explain why plants are quantized. Because what does it mean to be plants are quantized? Well, it means that basically if you look at a branch like this, okay, this right here is half a wavelength. the Wagner wave. And yes, this is the talk. And it turns out that some plants basically, they grow at these angles here, the branches, and they're quantized, but some of those angles don't meet the qualification, so they aren't included. And these Wagner waves, which are longitudinal, can also be polarized. Well, I had to go through the talk. And so, and it turns out he's just nuts. Completely harmless, but he was this older man doing physics in his backyard, and he had a book on cosmology and all these other things about Wagner waves. And he did his research with his son. And so the second talk was done by his son, who wasn't there. He just let Dad talk by himself. And so Dad had two sections of basically of this. And at some point, you don't want to laugh because you realize the man thinks he's actually done something. And I must admit, when this came out, this almost put me on the floor in hysterics. But you know, it's one of those where you want to go, but you don't, because he's honest. But all the crazy talks are there. So Wagner waves cannot be, if they're longitudinal, and assuming they exist, they still can't be polarized. There. So good to know. There's another guy who gave his name was EI Pi. So I've never seen EI Pi, but EI Pi had some really crazy talks too, but EI Pi never showed up. Yes.
I was gonna ask him, did the trees tell him this?
He discovered this all by himself. He discovered Wagner waves all by himself. Okay. And he has a cosmology based on Wagner waves and everything else. I assume he's dead now. I don't know, and I can't imagine the son kept on the research, the family research. I would really hope not, but okay. And he did this for years. There's just weirds of stuff. So when we do this like this, what do we have? So when I draw a wave like this, an EM wave. Okay, so here's my E, and here's my V. Will this wave here be linear polarized when I'm drawing it like that? Is that a polarized wave that I just drew? Is the E only oscillating in one direction?
Yeah.
Yeah, that would be an example of a polarized wave. This right here, this is polarized in this direction here. This is a polarized wave. Now, if you have a light bulb, the light coming from a light bulb is not linear polarized, or for most light sources. So light emitted from most light sources are not linear polarized. Let's say here's my light source. So let's say here's my little light bulb. So here's my little light bulb. That means the light coming in here, the way I'm going to represent this is the following. I'm going to draw it like this. This is going to be my representation for this. This is going to be unpolarized light. So what does that mean by, let's make sure we understand my symbol here. I'm saying the light's going this way, and what does this mean here? That you're going to have some waves are going to have the electric fields going like this. Well, what else are you going to have? Some ways the electric fields are like this, some are like this, some are like this. Each individual wave would be linear polarized, but if you look at the whole, all the light coming out, some are going like this, some are going like this, some are going like this, they're all over the map. That's what it means to be unpolarized light. Okay, that's my representation. Now the question is, how do we make this linear polarized? So how do we linear polarize light? And we use a linear polarizer. So simple. Diabolically simplistic. So we use a linear polarizer. And I want to show you how one of these work. This is an example of a linear polarizer. So like this is, I'll pass these around a little bit. This is linear polarizer. These are linear polarizers. These are all linear polarizers. Okay. I'm gonna say something. I'm gonna say something I rarely say in just a little bit. Okay. People have their calculators with them?
Calculators?
I know. It's like I'm going insane. Pull out your polar. We're gonna do something with your calculators here. Again, words that rarely come out of my mouth.
Oh, it's
Good
gonna
luck
put the filter on the calculator. and-
We're gonna see what we have about the light now. Let's figure out how we can make it, first of all, linear polarized. What we're gonna do is we're gonna take some plastic here. So this is plastic. Okay, what is plastic composed of?
Polymers.
Polymers. What is a polymer?
Organic material.
North, long chains of molecules. So what you're gonna do, you're gonna have this plastic and you're gonna heat it up. Okay, you heat it and you stretch it. Okay, so if you heat the plastic and then stretch it, what's gonna happen to the polymers? They're gonna basically stretch out like this. So you're gonna have these polymers like this. These are the polymers. And they're just long chains of molecules. And you're gonna dye you basically put a dye in here. So you basically, the plastic is heated, it's stretched, and dyed. Okay. The dye is gonna act like a source of electrons. The dye acts as a source of mobile electrons. Okay, so let's say I have now a wave coming this way. And let's say my electric field is like this. Okay. When that electric field hits an electron here, here's my electric field, here's my electron. What is that electron going to do then? And so the electric field is going up and down like that. What are the electrons going to do?
Move along.
Move up and down like that. And what are they going to do? They're going to lose their energy. Basically, that wave is going to do work on the electron going like that. And what's going to happen here is that wave is basically going to be extinguished because basically all the energy connected with the electric field here is doing work on the electrons going like this, and no or very little light will come. Okay, so what happens here is that very little light is emitted. Okay, it's basically most of the light, most of the energy associated with the E field is lost to friction as the electron is moved along the polymer chains. Okay. Now, what would happen if we had the following case? Same thing. All right, I'm like going this way, but now what I'm going to do is I'm going to have basically an electric field that is perpendicular like this. My polymer chains are like this. Now my electric field is going like that. So here you are, a little electron here. The electric field hits you this way like that. And what is not going to happen? There's going to be very little motion of that electron. There'll be some. Okay, but for the most part, that electron can't do much. So what is it going to do? That wave is going to go straight. What's going to happen here is that basically most of that wave will come out. That makes sense? So what does that mean? If you have then light coming at an angle like this, let's say my polymer chains are like this, I have light coming in like that, what's going to happen? What can I always do with the vector?
So keep going.
I can break it into components. The part parallel to that the polymer chains will do what? Get extinguished. The component perpendicular will go through. So what that means, if I have unpolarized light coming through, what I can do is I can always break any of those components up into part parallel to the chains and perpendicular to the chains, but the only part coming through will be
Perpendicular.
the perpendicular chains, okay? The angle at which the light comes out is called the transmission axis. The angle, let's say the axis in which the light exits the polarizer. It's a linear polarizer. It's called the transmission axis. So in this case here, the transmission axis would be this direction here. The transmission axis here would be like that, because that's allowing light to go through. That makes sense? Now, what would happen if I had two linear polarizers like this? So I have one linear polarizer here. So this would have a transmission, if here's my axis like this. Okay, so that would have let's do it better. Okay. So that would have a transmission axis like this. Okay, meaning light can get through this way. Okay. If I had unpolarized light like this, this is unpolarized. What's going to come out through here? Light like this, right? And this would be linear polarized. Okay, this object here is obviously called a linear polarizer. I just abbreviated it LP. You're gonna have a lot of LP. Well, if I have another linear polarizer like this, like that, what's going to come out?
Nothing.
Nothing come out. Because here the transmission axis is how? Transmission axis is this way. Okay. So what I'll do is I'll pass these around. If I look here, you can see me here. I can see here, these are two linear polarizers, but if I put these together and then if you turn them, at some point they go dark. Okay. Now what I want you to do, actually, okay, what I want you to do is, first of all, I'll pass it, you'll take two of them, go like this, and you can see it's cool. Then take your electronic device. Can't believe I'm saying this. Okay. Take just one of them and kind of go like this with it. Let's see if you can see something there. So,
Oh.
Two. Okay, you guys only got one. When you guys are done, pass them back to. Well, I'll show you how to tell whether the ratio is linear polarization. Oh, they are. Okay, that's cool. Okay, that'll work. So, what do you notice about your computer screen?
It turns like weirdly dark. No, like multicolored, like.
Well, there's going to be something funny is going to go on with that, and we'll talk about that. Okay. But what do you notice about your computer screen?
It's like the light is deep.
Okay. There is partially linear polarized.
Yeah.
It's either completely or partially. Okay, are you getting it to go out? Yes. Right here. And turn it.
Oh. I don't see anything.
Okay. Now, take it, if you have a linear polarizer, take it and look at glare. Look at glare on a table top on the floor and turn them on glare.
What?
What do you notice is happening with glare? Look at glare.
Glare.
Kind of shines through.
Is the glare going away?
No.
Look a little more carefully. Turn it, rotate it. Look at various glares. Okay.
Oh, yeah, actually,
Okay.
because you can read it
What are you noticing about glare?
going in.
It's gonna be partially going, we'll find out why later on. Okay, it's not an accident that glare goes away. In fact, the way you can, if you're buying polarized sunglasses or things that claim to be polarized sunglasses, what you're gonna do is you look at glare and you rotate it. If that glare does not go away, you're not buying a linear polarized, you're not buying polarized sunglasses. That's actually a very, very easy test. Okay, we'll find out later on why. It's actually gonna be connected to something called Brewster's angle, but we don't know that yet. Or the polarization of the studio.
My computer is like,
That makes sense? Yep.
What's it, I think that like sunglasses that are glass can be polarized, and maybe they can't, but what type of material would that use?
Well, there's like 1,000 different ways you can do this. Some of them, what they actually do is they actually have materials which are actually kind of like fine lines.
Wow.
Like that. There's like a zillion. This is actually the Polaroid technology. This is very old, but it's easy to explain.
Yeah.
What some of the new materials could be almost anything. Okay.
it's rainbow.
Okay. I'm going to show you something. I do it now.
Yes.
Okay. I don't necessarily have the.
More in the dark.
Like, oh, nice. What?
The reds.
There's blue. Oh, this one's blue.
Wait, those turn blue.
Should I turn blue? You can monkey with things too.
Everyone have polarizer?
Yeah. Why is the light turning blue?
I see the. No.
Then we have
Well, that's one we're just gonna, we also had artists.
fancy glasses.
Those are awesome.
Is that like,
They're polarized.
What do you just turn to?
Yeah, and it's too.
Oh, that's sick.
Impossible to have.
you should put full dark when you're driving?
That's one reason it's not legal to have. That's. It is. You have to have a permit.
We're still caught.
Maybe so.
The car. Driving.
Have you ever been like?
Fish. That I spoke to you.
No, mine too. Like, have you ever been in some car at night? Like rushing, and you're just like scared, dude. Like you have to call.
Okay, so this is this crazy material I call corn syrup. Okay, can I have some? I need one polarizer. Actually, I'll use one of the big ones. Okay, I'll turn off the lights. Okay. So let's do this. I'm going to put this up here and turn that around. What do you see happen?
It still keeps the same color?
Yeah, it's called dull. That's called bad experiment. It's called no fun. Okay, I'll do the following. Do the same thing.
Oh, wait.
What's happening?
Oh,
it turns green.
Keep rotating it.
it turned violet.
Keep rotating
See a
it.
lot of
Here, look at-
We see a lot of color.
Yeah, as you keep on turning it, what's happening?
color change.
Yeah, I can go like this. Rotate it. I'll turn it around so everyone can see it. Everyone see it?
Yeah.
Okay.
I just said.
Okay. So what's happening here is, what is that first linear polarizer doing? It's linearly polarizing light. So when it goes through here, I have one electric field going like this for all the colors. Now, what's going to happen here is that this right here is called an optically active material. And what it's going to do is going to take the electric field and it's going to actually rotate it. But how much it rotates it depends actually on the wavelength of light. So what's going to happen is that red light coming through is going to be rotated at a certain angle. Green light coming through will be rotated at a different angle. Blue light, all the different colors will come through at different angles. When you take your other linear polarizer here and you rotate it through, what are you doing? You're blocking out all those other components, only letting one component go through for the most part. What's happening is that as you rotate this, you saw it go through a whole bunch of different colors. Okay? All from humble little corn syrup. So did everyone see that happen?
Mhm.
Everyone could? Okay, so kind of cool.
I'd start here.
Did I make the joke that I'm at?
Later on, Alex, has anyone gone to Disney World? Okay, Disney, okay. Did you go to the Haunted Mansion?
I do not.
I don't like rides.
Which one is the highest? Oh, is that the?
Well, it's a Haunted Mansion. It's gonna be dark in some spots,
Yeah.
but I mean, it's, yeah, there more than things happen. It's dark. You know, there's a little bit more happening. There's a part where you actually see ghosts.
Yeah, okay, yeah.
And then you see the ghosts actually go through furniture and stuff like this. It's actually very, very dramatic. I went through as a kid as like 5 or something, scared the hell out of me. So, we'll explain later on how that works. It's actually a very old illusion. It's called Pepper's Ghost. And it's actually just, it's ridiculously simple. Like most of the magic, if you find out how magic is done, it's all ridiculously simple. And that's actually the beauty of it. Is that if you look at how it's done, it's utterly simplistic physics usually. Some stuff, and it's just very elegant. But we're not doing that. Okay, so what are we going to do with this? We're going to do the following. Let's figure out how the intensity changes when we pass through a linear voltage. So let's ask, if we send in light with an intensity I in into, is that showing up? No. Into a linear polarizer with a transmission axis at theta. Okay. What is the intensity I out of the emitted light? Okay. So what I'm going to have here is I'm going to have light. I'll say, which way do I want to do it? And so I'm going to have light like this. So here's my electric. And that's probably too faint to be seen. And here's my axis like this, and I'm going to say there's going to be a transmission axis like, don't want, yeah, I think I'll take this guy out. I'm going to say the transmission axis is like this. This is theta. The question is, what comes out? What is I out? If this is I in. Let me do another view of this just so you can get a better view of this. So imagine if I'm here. I'm looking this way, so I'm looking in on this. What I'm going to have here is that if here's my XY axis like this is X, this is Y. I'm going to see my transmission axis is like this. And this is forming an angle theta. I'm going to say that that electric field is oscillating up and down like that. Does that make sense? So I have the light coming in this way. The electric field is like this. I'm going to say the transmission axis is like that. I'm going to say the light coming into here is some I in. The question is, what is I out? Okay. Make sense? Now, let's remember what we know about intensity. What does intensity equal to? When we work it out, remember it was this 1/2. Well, there's some, doesn't matter with it, there's some stuff. And then what did it depend upon?
Something over area.
Something squared.
Where, yeah.
What's squared?
Okay.
The amplitude squared, right? This is basically this is the amplitude. Squared like that. That makes sense? Okay, now the stuff here, if you work it out, I'd have to work it, I think it's like 1/2 epsilon naught C. Don't quote me, I'd have to work it out. It's something like this. This is the stuff. So something like this, E naught squared. This E naught here, this is your amplitude. Okay. Now what's going to happen here? If I draw that picture here like this, here's my transmission axis. Here's my E naught here, like that. Here's my theta. Okay. What part gets through here? What can I always do with a vector?
Break it into components.
Break it into perpendicular components. I drop my little perpendicular here. Here's my E parallel. And here's my E perpendicular. Which component gets through?
E parallel.
E parallel. And this has to be this E naught. This goes in a theta. Right?
Mhm.
I square both sides. I multiply through by that stuff. Okay, whatever that is, doesn't matter what it is. Again, I think it's 1/2 epsilon naught C. Maybe there's a C squared there. But this stuff times this E parallel squared is
Your intensity coming out.
your intensity coming out. Hey, what is this stuff times E naught squared?
EF.
That's your E going in.
The
Times your cosine squared of theta. Boom. Yeah. This right here is called Malice's law. Sadly, since Latin is no longer taught in high school very much, I can't even make a nice Latin joke. But it's a good law. Hey, malice is Latin for bad. What's Latin for good? Bonus. So it should be called Bonus's law. But that, if you know Latin, that's just hysterical. Okay, that's just an utterly hysterical joke. It's brilliant. Okay. So we have Malice's law here. So what happens if you have, and again, this theta is what? Tell me what that theta is. That theta is the angle between the incident electric field and the transmission axis. So this theta here, this is the angle between the incident E field and the transmission axis of the linear polarizer, which I'll just start calling LP. Okay. Now the question is, what happens if we have unpolarized light going through a linear polarizer? So let's ask, what happens if we have unpolarized light of intensity I naught going through a linear polarizer set at any transmission axis angle. So I don't even care about how that transmission axis is set up. It can be anything. So you can have, if I draw this, here's my incident light. Again, my little Symbol for this is this. This is my I naught. I have my linear polarizer here. Let's say my transmission axis is here. The question is, what comes out? First of all, what's the only thing that can come out? Let's call this theta here. What is the only thing that can come out of a linear polarizer?
Something that is parallel to the.
So linear polarized light at the same angle as the transmission axis. That's the only thing that can come out of a linear polarizer. So this has to be linear polarized light, LPL, at theta. Now the question is, what's the intensity? I'm going to give you what it is, and I'm going to give you a plausibility argument for it. Okay, the intensity is going to be I naught over 2. So whenever you send an unpolarized light, some intensity here, that will always, the first one will always cut your intensity down by half. That's what it does. Now give me an argument for that.
Refractive index of the material?
And no refractive index. We're going to get to that in just a moment.
So what was the question again?
Give me an argument for why. Give me an argument for why this is cut down by half.
Because you can break it into perpendicular and parallel, and only the parallel gets served.
Yeah. So on average, what are you going to have happen then? You're going to lose basically half of your light, and so that's one of the arguments. Okay. Another one is the following: that if I were to look at that end view like this. So here's my transmission axis like this. What is my electric? I have my unpolarized light is this guy here. It's all over the map. Right, this is the light coming in here. Transmission axis is like that. The electric field is everywhere. So really, what are you doing? You're taking an average value of this guy here. What happens if I take the average value of this? This gives me I out. This gives me I in. What's the average value of cosine squared of theta?
1/2.
Is a half. That's another way to look at it. Okay, there's different ways to look at stuff. Now, with electronics, like with your, I have a friend who works at, I actually went to grad school together. And he, I didn't realize this. It says if you look at a lot of any of your modern screens, like any of these screens feel like this. What happens? You basically have light coming out that's being emitted, and the first thing you do is you want the light to be polarized, and so you have a linear polarizer there. Now, from an engineering point of view, that's actually kind of bad. Why? What have you done? Again, if you're an engineer, what do you want to do?
Reduce costs.
You want to reduce costs. What else?
Make it efficient.
Meaning that if you have a certain energy in there coming in, right, because you have the light getting in there, what do you not want to do? Lose half of it. Okay, so that's actually from an engineering point of view, that's already a bad thing. You're already losing half of your light. And so this is just something you want to think about with devices and stuff. Okay. So what happened if we had two of these coming in together? So let's say I have unpolarized light here. This is I naught. And have a linear polarizer here. Let's say that this is at an angle of 30 degrees. I have another linear, so this is linear polarizer. 30 degrees. I have another linear polarizer. Let's say this is at an angle here of 90 degrees. I have another linear polarizer. That's sad. That's at 20 degrees. Question is, what's the intensity coming out?
Let's do step by step.
I agree. Okay, so you take unpolarized light, send it through a linear polarizer, what do we get?
I've I know.
Okay, we have an intensity of I naught over 2. That's the intensity here coming out. And what kind of light?
Polarized.
At?
30 degrees.
Okay, and put in a linear polarized because we're gonna get right and left circular polarized light and right and left elliptically polarized light. So we're gonna say linearly polarized light at 30 degrees, because that's the only thing that can come out of linear. So now my electric field, if I were to draw it, would be like 30 degrees here. Now, this is coming into here, so what's coming out?
1/4.
Yeah,
Okay, let's know 1/4.
okay. So again,
I know.
we have I in, goes I out, cosine squared of theta. And tell me about this theta here. This theta is the angle between incident electric field and the transmission axis. So what's going, actually, this should be I out here.
60 degrees.
So the I in is,
I know over 2.
this is I naught over 2. This is what is coming out here. This is going to be I naught over 2 times the cosine squared of, now what angle does this electric field make with that transmission axis?
60 degrees.
60 degrees, right? Because here's my E. This is 30. This angle here is 60 degrees. So this is cosine of 60. What is cosine of 60?
2.
Let's try again. What is cosine of 60? What?
When I
Thank you. Okay. So this gives,
1/4.
Didn't I say
Then-
1/4?
okay.
Oh, okay.
Okay. What comes out over here?
Well, we
And
should.
I should say, yeah, and this is linear polarized light at 60 degrees. So you need two things. You need to tell the type of light and then the intensity. What's coming out over here?
Well, we just redo the same thing.
Okay, so it's linear polarized light at
40 degrees, 20 degrees.
always the same thing
Oh,
as the
20 degrees.
transmission, 20 degrees. Now what's the intensity then?
Uh,
I in is,
I now over 8,
and so it's a sine out over 8. Cosine squared of,
40 degrees.
70 degrees.
everyone agree? Is 70? Okay. Actually, yell at me here. Because this is not set up, this is not 60 degrees. This is, I saw the 60 here.
Oh, 9.
This is 90 degrees. Sorry about that.
Okay, so okay.
Okay, sorry. So then this is what? This is going to be linear polarized light at 20, but the theta is going to be the 70. Yeah. Right? Your electric field is like this. So you need that angle here, this theta equaling 70 degrees. And you have to work that out with the calculator. Okay, that makes sense? Questions? Now we're going to start sending things through some crystals. Let's ask what happens when light enters some material. We're going to spend a long time on this point, but this will be the beginning. So here's my material here. So here's my light. This is going to have some speed here, c. This is going to have some wavelength here. I'll call this lambda naught. This has some frequency f. So it's going to go in here, and what's going to happen here? First of all, what do you think is going to happen to the speed? That's going to decrease. So the wave is going to come in here. It's going to have some speed here, v. And it's going to have some new wavelength here. Let's call it lambda. And it turns out that what does that frequency represent is how much, it's basically the rate at which that electric field is oscillating up and down. That doesn't change when you go into the material. So the F here and the F here are both the same. Okay? What happens here? We define something called the index of refraction. We define something called the index of refraction for the material. And it's N, and it is by definition. I mean, probably the engineers know how we define it, or if you had physics in high school.
C over V.
This is speed of light in a vacuum over the V in the material. Now, what do we know about speed of light? This is F in terms of wavelength. What do you think we're going to find out about V in a material? It's going to be F times the wavelength still, it doesn't change, so it's F over lambda. Frequencies cancel. So what this tells me is that lambda equals lambda naught over n. Now, this n value, what does n, is n greater than 1 or less than 1?
Greater than one.
Yeah, n is going to be greater than 1, although we'll get into the case when it's not. Okay. And it'll never be negative?
No.
Evidently, there's some materials where it's actually some weird systems, I think, involving microwaves where you actually have a negative n. Well, that was my response.
That would involve a negative wavelength, right?
I haven't looked at the paper. I honestly don't know what it involves. I just realized like I wasn't ready for this. You know, my n has to be positive. I'm not ready for negative n. And I realize I just need to have some point in my life when I'm ready to actually look to see why n is negative.
Yeah, but that would imply a negative wavelength. Whoa.
I don't. It ends up implying something else that actually happens.
Oh, really?
And it just seems wrong. I have not read the paper. So n is going to be greater than 1, and what? Greater than or equal to 1. Well, I convinced you your material is going to slow up here. Now, I will convince you that that actually can be less than 1, but we'll find out what that means later on. We're not there yet, but it's going to be that. What are typical n values for like, let's say, water? This one you want to memorize. 1.33. Okay, for glass, there's no one value for glass. What was the typical glass value?
Ours is 2.8.
Really?
Yeah.
Oh,
That's it.
I'm thinking of more like just standard window glass and stuff like that. That's under like 1.5. Okay, diamond is gets up drone to something like that. So the point is that they're not going to vary a whole lot from 1, but they're going to be kind of on this order here. There's normally you don't have an index or a fraction of like 4,000. Okay, with a couple exceptions. Okay, one exception is when you have what's called a Bose-Einstein condensate. Now, what was a Bose-Einstein condensate from general physics? I mean, not from general physics, from modern physics.
Pretty sure it's a state like it's near the absolute zero.
Okay, you have a system that's very low. It's a bosonic system. What happens? All your particles being bosons that obey the exclusion principle. Remember, they all collapse into the ground state. An example, and that would be a Bose-Einstein condensate. So let's say you have a Bose-Einstein condensate and you send in light. When you actually calculate the index of refraction for these things, these indices of refraction are on the order of like, like thousands or millions, something utterly preposterous. Meaning that what is that light doing when it's going through that material? It's basically going like that through the materials. Okay, so you can get really, really bizarre values of n, but that's very exotic forms of n. Okay, everyday life, your n is going to be on the order of like 1, 2, something like that. Now, what we're going to do, we'll do this on Monday. We're going to take some materials that have an index of refraction in one direction and a different index of refraction in another direction. That's going to mean something. But what's it going to mean? So let's say I have one index of refraction this way. For another reason, if the electric field is this way, it's going to have one index of refraction. The electric field is this way, it's going to have another index of refraction. What happens if I have a light going in at an angle? What can I always do with the light? I can break it up into this component. I can break it up into this component. What are those two components going to do then?
Separate.
They're going to separate. You can separate in such a way that I can actually make that electric field when it comes out actually spin in a circle. If I set it up right, it doesn't have to spin in a circle, it can spin actually in an ellipse. Okay, so we can get elliptically polarized light, circularly polarized light. You can make it spin this way, you can make it spin this way. We can have right and left circular or elliptically polarized light. And that'll be for Monday. Have a good day.
Well, it's not.